Quick announcement. If you look at the syllabus, your lab test 2 is going to be October 29th. You still got about 12 days roughly. But I will give you some study guide next Monday the latest. I'll try to maybe make it available over the weekend. I'll try. If not, Monday the latest. Okay. So you know exactly what to expect for lab test 2. Okay, the plan for today. I would like to just review very quickly the asymptotic analysis, the mathematical part, very briefly, hopefully maximum 10 minutes. And then what we will do is, I'm going to do lots of examples with you. I'll do a simple example first to get a feel. Without counting the exact number of primitive operations, how can you decide the asymptotic upper bound for any algorithm? And then we'll do 2 more complicated case studies at the end. Okay, we'll see how that goes. Hopefully we can finish all those, and then there will be some new topic to cover after that. Okay, so now let me just review very quickly. This is the last example we did last time, on Monday. Okay, so now we know that from the previous slides, I gave you a strategy. Of course, you don't have to memorize the proof. The strategy was, if you're given a function over here, any function in general, polymorphic polynomial degree, which represents the runtime of your method or algorithm. You simply just figure out a big O by looking at the highest power in the polynomial, okay, whatever the highest power is. And so here's the proof. And the way you prove it is by choosing a C with the absolute value sum of all the multiplicative constants. And then N0, I would say almost 99% of the time that you will see should just be 1. There might be exceptions, okay? So now the example we did last time was the exception case. Okay, let's see why. So let's say if I give you something similar later, so let's say for this example here, 3 log n plus 2. So for log, if I didn't really mention explicitly in this course, it's going to be base 2, okay, not base 10. Okay, so now 3 log n plus 2. If we apply the same principle from the previous slides, we know that the sum of the absolute value for the multiplicative constant should be 3 plus 2, right? It's 5. However, in this case, N0 is not exactly 1. Okay? That's something I would like to just mention again, why it is not the case. Okay? So now let's just go. Basically, the idea is, if you want to show that the N0 cannot be 1, what you got to show is you have to apply this multiplicative constant 5 to the log n over here and show that when N0 is equal to 1, there's no upper bound effects. Okay? Let me just show you very quickly from last time. Okay, that will also summarize how you're supposed to judge everything. Okay, so this is the function we are talking about over here, 3 log n plus 2. Okay, we simply do 3 plus 2. So we just got 5 over here. Right? So we got 5 log n, and also we got the original running time function. So now when N0 is exactly equal to 1, we want to show that it does not have the upper bound effects. How do we show? Plug in the numbers. We know that log 1, doesn't matter what the base is, will just be 0. So now for this case over here, 3 times 0, 0 plus 2, you get 2, right? And then log 1 will just be 0, and then 0 multiplied by 5, you also get 0. So over here you can see 2 less than or equal to 0 is not the case. So that's why when N0 is equal to 1, it's not a starting point. So that's why you got to keep trying to the next one. Okay, any question about this example from last time? Okay, the idea is, whenever you apply that theorem there, you can definitely do the sum of the absolute value for the multiplicative constant. But for the starting point, for the upper bound effects, you got to be careful. It may not be just 1. Okay? I may want you to show me why it is not 1. Okay? So make sure you know how to do it. Okay? If you don't have any question, let's do one more, just to make sure you're okay. Just to warm up. What about this? 2 to the power of n plus 2. What's the big O? Huh?
No, I just had a question.
I just had a question. Yes, go ahead. Question.
Can you just repeat the importance of the upper bound?
Okay, the upper bound effects, let me just do it a slightly different way. You can definitely review the details. So the reason I'm really talking about upper bound effects, let's not forget, is from the very definition. Let me just show you exactly the slide you should look at when you study the notes. If you look at the very definition for big O, right? We want to show that, for example, any running time function you're interested, f of n, is actually big O of another function, g of n. Once you have chosen the C, if you want to show that it's going to start the upper bound effect with n0 being 1, So this is the equation over here. F of n less than or equal to c multiply g of n. Okay, that's the part you should look at, right? So this equation here must, this equation should really hold consistently towards the limits. Okay, good. Okay, now let's have a look at that example there very quickly. Okay, over here, big O of 2 to the power of n, right? Okay, can you see it? So for example, you can see here, 2 to the power of n plus 2 is equal to 2 to the power of n multiplied by 4, right? So 4, you can drop it. It's the multiplicative constant. So that's why you can see big O of 2 to the power of n, all right? And now, of course, you can try again to see if the upper bound effect is going to start from n0 equal to 1. That's something you can check very easily by applying the same, plugging in the number. Okay. One more. How about this? Be careful, since we got log. Okay, what is that? Big O of n. I agree. I agree. But now the question is the upper bound effect going to start from n0 being equal to 1? Is it or is it not? Well, easy, just plug in the number. When n0 is equal to 1, when n0 is equal to 1, what's going to happen? Oh, what constant would you choose? You would choose 2 plus, well, the sum of the multiplicative constant, right? In this case, it would be 2 plus 100, 102. Agree? If I choose 102, and then let's do this together. How about that? Okay, give me one moment. You can think about it quickly. Let me put it on my iPad and let's figure that out. So 2n plus 100 times log n, okay? How do we prove that it's big O of n, okay? Let's say choose the c being equal to the absolute value for the multiplicative constant. 2 plus 100 is 102. Okay, so now how do we show the upper bound effects? Let's see if that exists or not. Okay, put a table here. So you got 2n plus 100 times log n. And also you got 102, which is the c we chose, multiplied by n. So now let's see what n0 can be. Is 1 going to be the case for upper bound effects? Why don't we try? So 1 times 2, 2 plus 100 times 0, which is 2. And what about here? That's 102, right? So we do have it, okay? So it's not always the case that if there's a log, then n0 cannot be 1. It's not. So that's why you really got to draw this table and check it. So in this case, we do have the upper bound effects. So that's why if you go back to the slides over here, you can have n0 being 1. Okay? Okay, any questions? Okay, we're good. Okay, so now let me just mention some property very quickly over here. So now let's have a look. Let me just go to the previous slides here. So now this is the thing I would like to show you. The first line here is just a mathematical notation here. For those of you who took some set theory, so this symbol here means proper subset, which means we talk about the big O of some equation, some function. It's simply just a family or set of functions. For example, when I say big O of n to the power of 0 is a proper subset of big O of n to the power of 1, that means this collection over here on the right-hand side is strictly bigger. So there are certain functions that exist on this family here, but that does not exist in this family here. Okay, let's see one example. I'll just give you one. What about, okay, I do have an example there, but let me see what example I want to show. Okay, let's see this. Let me go back to the iPad here. Okay, let me share the space over here. Let me use a different color so you can see. Let's compare big O of n versus big O of n squared. Okay, as you can see, power of 1 is strictly smaller than power of 2. According to that, what we saw in the slides, the family for this is strictly bigger than the family of this. Okay, conceptually, this is how you draw, and then we'll see how exactly to figure out the contents. This is how you draw. I would say this is big O of n to the power of 1. Okay, And then we say strictly bigger over here is big O of n to the power of 2. Okay, let's consider different parts, okay? I would like to consider 3 things, okay? Can you give me one example over here? Which means there's, give me a function that is both big O of n1 and also big O of n2. One example. Anyone?
5.
I heard 5. Yeah, 5 is fine. 5 is bigger of n1 because you can definitely, well, basically if you just, 5 is a constant function. That means you can easily choose some very, you can choose C as being 5. You have the upper bound effects right away. What about 2n? Okay, 2n over here is big O of n1. Agree? And you can see that 2n over here is also big O of n squared. How do you see that? So 2n is big O of n squared. If you actually try to draw the curve, and you will see 2n is a little bit like this, you know, like this function over here, and n squared is basically much steeper, a little bit like that, right? So that's definitely have the upper bound effects, because whenever you got any strictly larger power, it's guaranteed to upper bounds that particular function, okay? Now, let's consider something similar. Can you give me a function that is here, but not here? Anyone? What about, yes? N squared. Well, n squared is good. Or 2n squared, right? Well, apparently, you can easily prove that 2n squared is big O of n squared by choosing maybe just 2, right? Something like that, or even 3. Now, when I say big O of n squared is big O of n, is this correct or not? No. Okay? Conceptually speaking, you can see that n squared can be something like this. This is n squared, like the red line over here. And then the blue line is more like an n over here. So there's no way you can have a very big constant, multiplicative constant that's going to have the upper bound effects towards the limits. It's just not possible because it's strictly larger power over here. So this is simply not correct. Okay, now one more. Can you give me one example that is going to be neither? We have seen function that is both big O of n and also big O of n squared. We have also seen a function that is n squared but not n. I want you to give me one that is neither. Well, good. What about 3 cubed? Which means there's no way for you to choose a large multiplicative constant for n squared so that it's going to upper bound this particular function because this has strictly higher power. Okay? So that's kind of the intuition you should get. All right. Now, what does that really mean? That means whenever you talk about a power over here, the power is, the bigger the family of function it is. And it's really strictly a proper subset relation here. Okay? Any questions about this? That's something you should know. Okay? All right, I assume silence means yes, right? Okay. Yeah, we get to more interesting stuff, you know, after the math. But how can you see the interesting, how can you appreciate interesting stuff before you see the dry stuff? All right, anyway, so this is the example I just mentioned, okay? Again, so be prepared to really, I give you any 2 functions like this, you should really give me an example like here, okay? The 3 kinds of example, just get prepared for that. Yep.
What if the power is like not an exact number or something like big O log n?
Log n?
Yeah.
So big of log n,
How does it like
yeah, big of a log n, basically something like this. It's definitely cheaper than big O of n, so it's a little bit like this. So big O of log n over here. Yeah, that's why it is. Good. All right. Okay, that's about it. And then I want to go through one more things you should know, theoretically speaking. So now this is the thing. Whenever you talk about the asymptotic upper bound for your method, you want to be as accurate as possible. So what do I mean by this? let's go back to this diagram here. So this is the most important intuition you should get from this diagram. When I talk about, for example, this particular function, 2n, okay, let's focus on this one here, 2n. It is correct when I say 2n is big O of n, right? That's in this family here. It is also correct when I say 2n, the same function is big O of n squared. Agree? That's also a member of this bigger family. Okay? And you wouldn't be too surprised if I say it is also big O of n cubed. So 1, 2, and 3, all of them are just as, they're all true. They're all correct. However, for example, these two are not very useful. You can see when I say 2n is big O of n squared, and when I say 2n is big O of n cubed, even though it is correct, but it's not very useful. The reason that we want to really know the asymptotic upper bound is to judge which algorithm is more efficient. But if you simply do things like this, you know what you can do? You can say every algorithm we have is simply big O of 2 to the power of n. Okay, that's the extreme case. Since we talk about the worst case, but so you can go as worse as this, even though in practice it's not possible. Okay, so now go back to the slides over here. So you want to get as close as possible. Let's see more example. Let's see this. I got f of n is 4n cubed plus 3n squared plus 5. So now, what's the most accurate one? N cubed. You should choose the exactly the highest power, right? However, you can see that, remember from the previous slide, we say the family for n cubed is strictly smaller than the family of n to the power 4, and etc. So that means the same function should also be a member of big O of n to the power 4, right? Because it's strictly bigger family, so that's also there. But it's most useful when you just give the tightest bound, okay? That's the point, okay? Okay, however, you shouldn't go lower the other direction. When you say this function over here is big O of n to the power of 2, that's simply not right, okay? So now what you have to distinguish between is when you say something that's true, or when you say something is true but not so accurate. So that's the point of these slides, okay? Of course, whenever I ask you to determine the bound for any method, you should give the most accurate one. Okay, you can see other example over here. Okay, any questions about this? Yes.
So you said don't include the constant factors.
Yes. Yeah.
But like, could it be useful? Like, wouldn't it be useful to specify which ones it would be? Because like 100n is going to take a lot longer.
Yeah, exactly. So what Jordan's question was, let's say if I got these two comparison. Let's say you got, for example, big O of 100n versus big O of, let's say, 2n, right? Basically, right? You're right, in practice, maybe having 100 primitive operations to execute is definitely much more expensive than only 2 primitive operations to execute. But since we talk about, mathematically speaking, towards the limits. So whenever you talk about big O, that's really towards the limit. When you say towards the limits, 100 times versus 2 times really doesn't matter. Yeah, but you're right, in practice, yes. Yeah, yeah, good. All right. Okay, one more thing to mention. So these are the typical classes of function you will see. Okay, we actually have gone through these already. The cheapest one you will always want to have, even though it's not so possible always, is constant function. Okay, which means regardless of the input size, you always get a constant number of primitive operations to execute. And you go all the way from log n to n log n. And n log n is a very interesting running time to have. I hope to cover something called merge sort when we talk about recursion. Okay? Remember the arrays.sort method we use, right, for the compare to, which you may have to use for the lab number 3. That's something to do with n log n. A little bit preview. Hopefully I can cover that a little bit later. And we also got n squared, which we will see quite a bit today. N cubed, also n to any power. Okay? And then eventually get to exponential. You don't really want to get to exponential. That's too expensive. Okay? All right, and that diagram simply shows you if you got constant function, it's the cheapest one because the slope is completely flat. But if you actually got maybe some the more expensive the function is, the steeper it is for the curve towards the limits. Okay, that's kind of the idea. Okay, that's about the math part up to now, before we see examples. Okay. Any questions about this? Okay, now let's apply our knowledge to examples. Okay, let's start from something very simple. Okay, first one. Now, I'll give you this piece of code. I would like you to tell me. So now let's say the following. It would be very nice if you can just calculate the precise number of primitive operations. But since we also talk about big O, so having 7n minus 2 versus you got 7n plus 5, asymptotically speaking, is really the same. So I would say unless really necessary, otherwise when we want to just determine the asymptotic upper bound, you can just approximate. Okay? So we don't have to know exactly how many, precisely how many primitive operation we need to execute. Okay, it's a different practice. Okay, how about this? Can you see what's the asymptotic upper bound? This one here. Could it be a quadratic algorithm? Okay, logarithmic? No? What is that? Anyone? Yes. Constant. Okay. Actually, how can you get intuition? You can see you only got if conditional. There's no method call, so that means there's no uncertainty here. There's no loop. I would say typically your code might be expensive if you have a loop, right? So now, nothing here. So it's simply just basically counting the primitive operation. You will see just constant. Okay, always the same. Okay, if you really want to count, you will count exactly 4. And 4 is big O of 1. Okay, so that's simply just constant algorithm. So this one is easy. Oh, this one we have seen. So if you just try to apply what we did before, it's going to be 7n minus 2. So that will be just be big O of n. Okay, it's a linear algorithm. This one is also easy. Okay, we have seen. This one is new. Okay, how about this? Let's tell me the big O first before I show you how you can approximate. When I say approximate, of course, you cannot just say, oh, because I think it's big O of n squared. No. Or you simply tell, oh, because there's a nested loop. No. You're going to somehow, have some judgment there. Okay? But just tell me what you think the answer is. Big O of n to the power of, I heard 2. Okay. That's a good guess. Okay, it's big O of 2. But how do we see that, right? That's the thing. So contains duplicate, again, you can see over here, n over here is simply the size of the input, okay? Let's try to see the following. Whenever you have a loop or nested loop, the best way to figure that out is, first of all, look at the loop body and see how expensive the loop body is. And then you will look at how many times that particular loop body will be executed, okay? Let's just follow that logic there. Let's see over here. The body of the loop apparently is over here. Okay, these two lines over here. We say if something, and then I will return true, which means there is a possibility before I actually go through all the possible indices for the array, I might just say return true and exit from the code, right? That's one possibility. But since we talk about worst case scenario, so let's assume we always go to the end of the method, in which case it's just not line number 8. Let's assume. Okay? Let's assume we'll always execute this line over here, but we'll not actually get into this part for the worst case. If that's the case, if you look at what we are doing here inside the loop, let's try to see that. You can see we are trying to check something over here, and also calculate something like that. So these are simply just primitive operations, aren't they? Okay? Just big O of 1 for these checks. And return, let's assume we don't really get there to have some early exit. Let's say we always go to the end for the worst case. What about J++? Well, we know very well it's also constant, right? Big O of 1. And this part also is big O of 1, right? So far we can see, as long as we know exactly how many times we're going to execute these constant operations, then we'll get the answer. But now it's to figure out exactly how many times we'll execute the body. Okay, how do we figure that out? You got to look at the loop counter. Okay, let's see. So we got line number 2 here, that's the outer loop. Line number 3, that's the inner loop. Okay, and we got actually 2 loop counters. Okay, so now let's try, since you understand nested loop should be pretty well from your 1022, let's go a little bit faster here. Okay, let's try to do this pattern here. Let's talk about the value for I. What are the possible values for I? It can be 0, can be 1, can be 2, all the way up to n minus 1. Good, thank you. 0, and then 1, and then 2, and all the way to n minus 1. Okay, so now, specifically speaking, when I is equal to 0, what can be the value for j? So I'm talking about going here, right? How many possible values are there for j? Yeah, was also n, right? From 0 until n minus 1, right? Okay, so that means for j value there, it can be 0, can be 1, all the way to n minus 1. Agree? For j. Okay, let's do one more. When I increment its value for the second iteration for the outer loop, what we get is, over here, for when I is equal to 1, what about j's value? Is it going to be wider range, narrow range, or the same? The same. Pretty good. So that means 0 until n minus 1. Hopefully you see the pattern now. That means, what's the size for this range over here? N. And then, for every possible value for I, we have to go over this many possible values for j. And then for every possible combination of I and j, we have to execute the body over here. And the body itself takes constant time. So what does that boil down into? That means, let's see this. Big O of 1, this is the body of the loop. We know that it's constant. Multiply by n over here, the possible value, let me just be more precise, possible value of j for each I, right? And also, how many possible values do we have for I? It's also n. It's actually n, right? From 0 to n minus 1, yes. Okay, and then these are all the possible value for j. I. Possible value for I. And that's how you calculate, approximate. So I'm not asking you to calculate precisely, but it's going to be good enough. So what do we have? It's going to be big O of n squared. So your first guess was right, but if you want to justify, that's more or less what you have to do. So how do you justify? You have to explain to me how you see the patterns for how many executions there should be for the body of the loop. Okay? Any question about this? So of course you have done this a lot, maybe in your lab number 1 about the matrix, right? Lab 1 part 2. Yeah. Yes.
So just to clarify,
Yes.
before the body execute,
Give me a line number.
or like just in general.
Yeah.
Like counting like n minus 1 times n minus 1. That's how many times the body is executed. But check it like n.
Yeah, I see what you mean. Basically, maybe you're slightly bothered by, remember the example we did for calculating the precise number of primitive operations. I asked you how many times the state condition will be checked, it's actually n. And also how many times the body of the loop will be executed is n minus 1. Remember now we talk about asymptotic upper bounds. So n versus n minus 1 doesn't quite matter. It only matters if I ask you explicitly to count exactly how many primitive operations there are. If I didn't say that, simply give me the tightest asymptotic upper bound, then you can approximate like this. Okay? +1, off 1, or even off 2 is okay. It doesn't really matter. Because all the multiplicative constants, all the lower terms, doesn't matter anymore. When you talk about limits. Okay, this one is good. Any questions about this before we see something else? Good. Okay, this one here, basically big O of n squared is quadratic. What about this? Let me pose the question to you. Would it be quadratic or cubic? How many for loops do we have over here?
1, 2, 3.
Yeah, I used to have one student, not at York. I used to have one student, they simply told me, oh, they simply just calculate how many loops you have. And then whatever number you get will be n to the power of that. No, right? Apparently that's a counter example. So this wouldn't be n to the power of 3, apparently, right? You had to see exactly how you organize the loops together. How do you think this should be? Okay? And a student told me that it should be n to the power of 3 because n plus n to the power of 2 is n to the power of 3. Is that right? No, right? Okay, good, good. Please don't make that mistake. Oh, in case you don't catch this, okay. Let me just show you. Okay, let's see, and then I'll tell you what my ex-student actually used to say. Okay, over here. So now, over here, this is something we know pretty well. Just figure out the max. This one is big O of n. And then, since it's not nested, so we're going to say in parallel, one after the other. And this one, we know that it's going to be big O of n squared. And this one is simply just constant. I can say big O of 1. And then this one is a big O of 1. Okay, they are just lower terms, so we can we don't have to worry about them. Basically, big O of n plus n squared. And big O of n cubed. Okay, good. N squared. Just make sure when you do addition, you don't just add up the powers, please. Okay, n squared. Because this is considered lower term, you can drop it. Okay? Yeah, this example basically just shows you don't just count the number of for loops you have. You got to see the structure. Okay. Okay, any question about this one here? Okay? If no, let's see another one. What about this? This one here, you might take a guess, first of all. Huh? Quadratic? I heard one now, yeah? Okay, I tell you why it's quadratic. Your intuition is right. Somehow we have a nested loop, and the way we increment the loop counter, etc., seems to be reasonable to be a quadratic algorithm. However, the justification wouldn't be so the same as what we did as a previous one. I would say it's similar. Okay? In the previous one, we're basically saying for each value for I, you got the same number of value for j to go through. Okay? But is that the case in this case? Okay, I heard no, that's good. Okay, why don't we have a look at that together? Okay, and somehow this gives you a little bit hints, triangular, but if you don't see it, that's okay. Why don't we see it together, okay? Again, let's go line by line. What would be the asymptotic upper bound for this line over here? Constant, right? Big O of 1. Okay, let me just do the final one, which is outside the loop. This is also big O of 1. So this is the part we have to worry about. Okay? And then let's look at the body of the loop, which is over here. And what is that? Oh, guys, why don't you tell me? Why don't you tell me? Okay? You didn't miss the important part yet. All right? What about line number 5? Is that constant? Yeah, it is constant. All right? So that means the asymptotic upper bounds for this nested loop over here is going to be the number of iterations times the time that takes to execute the body for the loop, right? And we know that this part here is already constant. So now all we got to do is figure out exactly how many times we're going to execute the body of the loop. So now again, let's figure out the patterns for the loop indices. Let's figure that out. Okay, let's do a similar exercise over here. Let's say I and j, right? When i's value can be 0, can be 1, can be 2, all the way to n minus 1, all the way, right? In the case where I is equal to 0, what can be j's value for the inner loop? 0 up to n minus 1. Very good, I agree. 0 up to n minus 1. So we got, in total, n possibilities, right? Very good. What about the next one? Okay, so yeah, good. Starting value is 1. And then because it's assigned to I, 1 up to n minus 1. So we don't get exactly the same, right? So that would be n minus 1. Okay, hopefully you see the pattern here. What about the very last iteration over here? So now j is going to be just 1, right? Why? Because when j is assigned to this particular value of I, which is going to be n minus 1, n minus 1 less than n will be true, but when you go to the next iteration for the nested loop, or for the inner loop, it's going to be n, which less than n will be false, so that one doesn't count. Okay, it's going to be just 1, just n minus 1. Okay, so we got something called arithmetic sequence, right? So you got n plus n minus 1 plus all the way to 1. What is that? N squared. Good. Of course, you can simply say that's simply big O of n squared. That's okay. In case you don't know the formula, the front plus the end multiply number of terms divided by 2. Right? That's what you learned in the high school. Okay? That would be big O of n squared. So this is actually very useful sequence for you to know. Very useful. Okay, any question about this? So the lesson learned from this slide over here is, even though, let's contrast. If you compare this slide over here, which is n squared, with this slide here, which is also n squared, even though asymptotically speaking, they are the same, but the way you justify is a little bit different. Okay? I have a general question for you. Let me put it on the iPad before we talk about some other example. Let me say add page below. Let's say this, just in general. If I have some integer array A, let's say I have a method over here. Okay, just take one argument, and then that's the size of the input over here. Now, if I simply say I have a single loop over here, only a single, not nested, only a single loop. Can you always say it's always going to be big O of n, the most? Can you say that? Depending on contents, I like that. Can you give me one example where I don't have any nested loop, but somehow the loop, maybe what you're talking about is over here, right? Or the body, doesn't matter. Give me one example where I don't have any nested loop, but the running time is going to be more expensive than linear. Okay, in general, is that the case? I can tell you it's not. Okay, but can you give me one example? Exponents? Wow, that's infinite, right? Basically, you talk about infinite loop, right? Yeah, that's that's interesting, to be honest. So basically, what you're trying to say is you simply just put true. Yeah, first of all, whenever you see any algorithm like this, you know it's bad, right? You don't want any infinite loop, right? I agree with you.
And usually they put break or something.
A break or something, yeah. Anyway, okay, let's not distract. Anyway, so now can anybody come up with one, just play with the loop pattern or at the body of the loop, no nested loop. Can you give me any example where the running time is going to be more expensive than linear? Sorry, say that again? Put n? Oh, you're saying this, right? Call n itself, you mean say, I tell you why it's also infinite. As we'll learn later in the recursion case, this is kind of infinite recursion, which is as bad as when you say while true. Okay, let's not worry about that either. Guys, it's a very simple answer. Okay, anyone? Yes, go ahead. Mm-hmm. How? How do you manipulate? Well, you're right. We're going to manipulate the loop counter in a way. I agree with you, but how exactly? Can you multiply? But if you multiply your n by 2, that means 2n. 2n and n, asymptotic spin, they're the same. You're getting, yeah, you're getting somewhere. Yeah. Yeah, that's right. Okay, how about this? I is assigned to 0. I plus plus as usual, by here I say I less than n to the power of 2. Right? That'll give you quadratic. Agree? Because if you simply, well, let's say this part is simply big of 1 for the body of the loop. How many times are going to execute it? N squared. In that case, you still get an N squared algorithm. So the lesson is, don't just count the number of loops or how they are nested. You should really observe how the loop counter actually change. Okay, so this one overall is going to be big O of N squared. Okay, just because you're going to run this many times. Okay, good. If no question, I would like to bring us our attention to some very interesting algorithm. Remember, I promised what I would do is I'm going to show you some sorting algorithm. So let me present to you the problem. Let me get to the problem once we get there. But this slide here just get you warm up a little bit. Okay, again. We talk about arrays. Since we talk about asymptotic upper bounds, let's see the various operations we can perform on an array. So we know which one's cheaper, which one's more expensive. Okay. So the array is a sequence of index elements, and then size of the array is fixed. Good. So now let's see the various operations. If you just want access to an array, let's say something like this, what will be the asymptotic upper bound? Constant. Very good. Big O of 1. That's easy. What about updating a particular index? Seems to be also constant, right? All right, good. Now, what about you want to insert something to an array? Let's say I have a little bit like let's say I have an array of size 10. I have already filled in 10 elements into the array. Now I want to insert an 11th element into it. How expensive would it be? Still 1? Remember, well, let's see this. Let me just visualize this quickly. Let's say you have this. I have an array of size, let's say 5, for example. I already got, let's say, all the numbers here. I say 2, 3, 1, 4, 6. Okay? I already filled in all the spots I have available. But now I would like to insert one more number. I don't have space. And I don't want to delete any of the numbers at the moment. So now, what would be the cost in order to do it? Conceptually, let's say I want to insert another number called 7, for example, right? So what I expect to happen is I should have, after the operation, 2 should be still here, 3, 1, 4, 6. All number that used to exist should still exist. And now I want to put 7 here. So transforming this array to this array, expensive or not expensive? Expensive. How expensive is that? N, okay, good intuition, okay, that's N. Because think about this, what are you going to do? Conceptually, you have to create, first of all, create an array of +1 size, and then copy everything over from the old array to the new array, and then insert the element into the new array, right? So when you do the copy, it's going to be a loop, and that will be a linear time. Okay, let's do one example very similar to that. Okay, let's go over that together. Okay, let's have a look at the code. Don't worry about the example below. Okay, let's go step by step. This is what we want to have. Let's say over here. Maybe yellow is better. Okay, so let's say we have insert add a method. We take a string array as input, the size of the array. We take a single string value, and we say at which index will we want to insert the new string value into. Okay, and then we're going to return a new array. Okay, for example, if I say insert add, let's say I already got an array with Alan, Mark, and Tom, like A over here. I want to insert, of size 3, of course. I want to insert a new element called Jim at position 1. Okay, what does that mean? That means, let's imagine what's going to happen here. Somehow, what would be the steps over here? Of course, it's already in the code. Can you describe to me conceptually what's going to happen over here? If I want to insert into index 1, that means every element that used to be before index 1, they should remain unchanged on their positions, right, in the new array. And then everything that occurs at index 1 and onwards, they should be shifted to the right by 1 position. Conceptually, that's the case. Okay? And when you say shift to the right, that sounds like a loop, right? And when you say everything that happens before this index should be copied over to the new array, that's also another loop. Okay? But should the loop be nested or should be one after the other? One after the other, right? Let's have a look very quickly. Okay? Conceptually, that's the idea. Let's have a look together with the example. Basically, this is what we're going to do. I'm going to do a little bit jumping for the code. Okay? Let's see here. The middle step over here is we say results at position I is assigned to E. Now, in this case over here, let me just do some replacement here. So A over here is simply this array, and then size is 3. And element over here is Jim. And then we want to insert into index 1. Let's say that's what we want to do. Okay? And then we simply, first of all, in the first step, we create a new array, and then eventually return it. And what should be the size of the new array? It should be n plus 1. Used to be 3, and the return value should be 4. So now that's why I got an array of size 4 over here. Now, let me just talk about the middle step first. We know that this is a new element I would like to insert into the array, exactly at index I. So index I should be index 1. Index 1 over here should be Jin. So that's exactly what that line is doing. Just this line here. What's the cost for that line? 1. Constant. Thank you. Good. What about before that? That means everything that goes before index I minus 1, I should copy them over, right? For example, Alan happens before index 1. That means I should really just copy Alan over to index 0 over here. There's only one element that happens before index 1, so only one to copy in this case. Okay? Now, what about, so this one here, but what would be the worst case for the first stage? If I say insert at index maybe 2, in that case, there will be many more elements that happens before the index, so you got more to copy over in the first stage, right? So in the worst case, it can just be linear, right? So that's why this loop over here will just be linear, big O of n. Because I minus 1 over here, I'll just put a note here. So the worst case is I is simply equal to n, very close to n. Okay, that's the worst case. Let's just see one more programming trick. So we talk about the middle part over here. We talk about what happens before. What about this line over here for the for loop? Basically, what we're doing is, since we are inserting the new element Jim at index 1, and we still want to keep the old elements in the array, that means everything that start with index 1 over here, they should be shifted to the right by 1 position. Conceptually, what used to be at index 1 over here should now go to index 2. What used to be at index 2 should now go to index 3. Right? That's why you see exactly this line over here. Okay? So that's why you have to say, for example, result, let me just give you one example, result at position 2 over here should be assigned to the input array A at position 1. Okay? And also result at position 3, which is over here, should be input at position 2, right, over here. You can see there's one difference in between the indices, right? That's why you see the j minus 1 over here. Okay, that's about the detail. So you just put Mark here, and also Tom here. Now, similar analysis. What would be the asymptotic upper bound for this third stage? Seems to be similar to the first stage, right? You can see you also get a loop. And what would be the worst case for this case? We said that for the very first stage, the worst case is when the I value is kind of large towards the end. That means you got more work to copy over before the shift. But now, what would be the worst case for this third stage? It's kind of symmetric, right? That means I is simply very small. For example, when I is, for this part over here, the worst case is simply when I, for example, is simply equal to 0. What does that mean when I is equal to 0? That means I want to insert a new element into position 0. Everything that happens at position 0 and onwards towards the end should be shifted all the way to the right by 1 position. That means you got to copy over everything to the right to the new array. So that's the worst case. So the worst case can still be linear. So now what can we sum up the performance? Okay? What we can do is, let's just highlight what we have got so far. So we got big O of n for the first stage, big O of 1 for the second stage. We also got big O of n for the third stage. If you add them up together, that'll be big O of n. Okay? That's how you justify. Okay? Overall, it's just big O of n. Questions? Have you guys follow? Okay, are we good? Okay, if you're okay, so let's go on. All right, time complexity would just be linear. Now, here comes the sorting. Let me present to you the problem first, what the sorting problem is really about, and then I'll give you two solutions. And then what we want to conclude at the end is to see which one is more efficient, or they might be the same. Don't know yet. Okay, let's see what the problem is. The input is just going to be an array of numbers. Okay, we just have an array with maybe n numbers. Okay, it can be 100, it can be 1,000, it can be 1 million, doesn't matter. And then with the output is going to be, when I say permutation, permutation simply means all the numbers should still be in the output array, but it's going to be arranged in an ascending order. Okay, then we just, for example, if you got, let me see what example I have, 3142. For example, for the sorting, if the input is simply like 3142, let's say if this is the input over here, and the output is going to be basically just another array of the same size. All the elements that used to be there in the input should still be there in the output, but it's going to be rearranged accordingly, right? So now it's going to be 1, 2, 3, 4, okay, like a sorted. But now the problem is, how do we go from input to the output, right? To understand the relationship between the input and output is easy, but how you actually achieve that is difficult, right? So that's what I'm going to show you. There are two ways, at least, to do it, okay? Okay, that's about the problem. Let's see what the solution can be. Okay, we'll propose two different approaches, okay? What I would like to do is, I will talk about, for each one of them, I'll first give you the idea conceptually, and just from the concept without seeing any code, we would like to guess what the asymptotic upper bound is. After that, we'll see the code in Java, and then we'll trace the code a little bit to get some idea. I think these will be good case studies for you to figure out the big O. Okay, so selection sort, I would like to talk about first. After selection sort, there's another sort called insertion sort. Selection or insertion. Okay, let's see one by one. Okay, selection sort. First of all, let's say we consider the same input array. Let's say we got 3142. That's the input. It's not sorted yet. It's just not. Okay, let's get some idea how to sort it using selection sort. And there's some convention I'm going to use. Let me use highlighter over here. Whenever a part of the array is already sorted, I'm going to use green. Any part that's not sorted yet, I'll use red. Okay? Initially, everything should just be red. Initially, because nothing has been sorted. Nothing. Okay? The idea is we want to proceed with our algorithm so that eventually the whole array is green. That's the idea. So the whole everything's sorted. So now the idea about selection sort is very easy. You want to somehow grow the green area one element by one element each time for each iteration. How do you grow the green area each time? You simply select the minimum number from the red area. Does that make sense to you? Maybe not, right? Let's see how that works. It works incredibly well. So the reason that it's called selection sort is you keep selecting the minimum from the red area until you have nothing else to select from the red area. And then the green area is your solution. Let's see how that works, okay? In the beginning, everything is in red area, okay? So now, if I try to do step number 1, over here, do step number 1, what would be the minimum value for me? 1, right? I still have this array over here. 1, 2, 4 elements. I know the minimum value is simply just 1. I'll put 1 to the left, and then put everything else to the right. Okay, what does that mean? That means what we have done is something like this. This part is unsorted, and this part is sorted. Are we okay with the first step? You can see from initial input to after the first step, we have grown the green area by 1 element. We have shrunk the red area by 1 element, right? Keep doing this. Okay, let's see one more. If I want to do another one, second step. If I try to do second step, the one over here is already fixed. It's sorted already. I will choose, again, the minimum. In this case, it will be 2, right? By the way, what would be the time complexity to choose the minimum? I heard linear. Okay, we'll get there when we talk about the time complexity. Okay, so now it's going to be, again, the same array of size 4. Over here, 1 is already there. We don't touch it. And now we're going to choose the minimum, which is 2. Once you choose the minimum, put it right to the end of the green area. We grow it by another 1. And then the rest, simply put them here. So what have we done? Basically, over here, 1, 2 is the sorted part. And over here, 3, 4 is the unsorted part. Okay? So far, so good? Okay? That's exactly what the code is supposed to do. I'm just trying to present in a more conceptual way, more higher level. Okay, let's do one more. And now, after this step over here, what's going to be the case? We're going to grow the green area by 1 more element, so 1, 2 doesn't change. And now choose the minimum from 3 and 4. Well, in this case, easy, just 3. Okay, 3 here, and then 4 here doesn't change. So that means we have over here 1, 2, 3 over here, and also we have 4 over here. We're not done yet, right? Because the red area is not empty yet. Okay, let's do one more. Okay, after this, like that. So what we get is, what's the minimum now for the red area? Well, just 4, because there's only 1 element, so it's trivial to solve it. So 1, 2, 3, and 4. So what we have done is, now the red area is gone. Everything's green. Guys, are you okay with the conceptual steps, each one of them? Okay? Keep selecting the minimum, basically. Keep selecting. And what's going to be the relationship between the very first minimum I choose and the very second minimum I choose? What's the relationship? The first one is smaller than the second one. Can it be the other way around? If it should be the other way around, I would have chosen that one, right? Right? Okay, that's kind of the mathematical insight into it. You keep choosing the minimum. So it's guaranteed all the sequence of minimums you have chosen should be arranged in an ascending order. Okay. So now let's talk about running time. Okay. Now, what about running time? Conceptually, what should be the running time to you? Well, n squared, okay, sure, but how did you figure it out?
Because the first array is assignment, right? And we know that the minimum function it's ordered, right?
Yeah, correct.
Right. So now you go to the next step, and you have n minus 1. You're raised to n minus 1, so it's going to take n minus 1.
Okay, very good. That's exactly right. Okay, let's see a little bit more the case. Okay. So now let's see this. For this particular example here, how many iterations would it take for me to figure out the minimum for this array? How many iterations would I take? In this case, depending on the size of the array, right? In this case, I'm going to choose from an array of size 4. So that's going to be 4. What about to choose from the minimum from this particular subarray over here? 3. Strictly smaller array, so that should be 3. And the next one is going to be 2. And then the next one is going to be 1. Okay, so it's kind of similar to our triangular sum, right? A little bit similar. Okay, let's see in general, very quickly, in general. If you have an array that looks like this, doesn't matter how large it is, starting with green, okay, initially. let me just use color here. Maybe, let's say for the let's say oh, that's not what I meant to draw. Let me do it again. This is our input array. Doesn't matter how large it is. And then we start with everything just unsorted initially. Okay, so now if we want to go from here to the second step, we know that what's going to happen is only the first elements over here is going to contribute to the green area, only the first one, because only after the very first iteration. So that means the remaining part is still going to be unsorted, right? So now the question is, to go from here to here, how much does it cost in order to figure out the minimum? Let's say this is 0, index 0, and the last element is index n-1. How much does it cost to figure out the minimum for the very first initial array? N, right? Because the size is n, you have to go through the entire array in order to figure out the minimum, right? So that would be n, bigger of n, to get the minimum. Okay? One more. What about the second iteration? After the second iteration, we know that what's going to happen is we're going to have the first two elements as green. And then the remaining part will be red. Okay? How do we go from here to here? We actually have to figure out the minimum for this particular subarray. And what's the size of that? Would that be n? n-1, right? Good. So that should be n-1. So it's big of n-1 to get a minimum, okay? And etc. So now let's go to the last one, the second last one. The second last one should look something like this.
The toolbar is almost green.
Exactly. Let me just draw it, so make sure. Okay, we know that this is the last one. The last one should be everything's green, basically. And the second last one should be something like this. Almost everything's green, except for the last slot is actually red over here. Right? So now if you want to go from here to here to figure out the minimum, well, it's trivial, right? Just that number right away. So it's going to be 1. So now what we get is, in general, if the input size is simply just n, for the very first time for selection, it will take n time to actually to get a minimum. So big O of n for the first time, and then the second time is going to be n-1. n-1 plus all the way to 1. So that's the running time for selection sort. Okay, what would that be? N squared, right? That's kind of the sum we are used to. So that would just be big O of n squared. Okay, so that's the conclusion. So we haven't seen any code yet. So you can see the advantage of having having the knowledge about asymptotic analysis is, even when I talk about high-level idea like this, we can already figure out the running time before we see the code. Okay? Hopefully you see that advantage. If you want to do experiments, you definitely want to write some working Java code before you can see the time. Okay? Okay, guys, any question about selection sort conceptually? Okay? What I'd like to do next is to talk about insertion sort to compare conceptually before we see the code. Okay? Let's see insertion before I see the code. We'll see the code in just a moment. So now the same array over here, but now we're going to see how insertion sort is going to work. Okay? Insertion sort works in a symmetric way. You can see over here, when we have so many, how many selections in overall? How many selections? How many selections for us to make? Well, depends on how large the array is, right? If we got an array of size n, that means we have to make n selections. So that'll be n selections. Okay? Out of the n selections, which one is the most expensive selection? The first one, the third one, or the last one? The first one, right? The first one is you have to select from the whole area for the minimum. That's the most expensive one. And then the cost decreases until when we go to the last selection, it's just trivial, just 1. Insertion sort works in a symmetric way, which means the first insertion is going to be the cheapest. and the last insertion is going to be the most expensive, just symmetric. Okay, that's something I want to tell you first before we show you conceptually the idea. Okay, let's have a look at that. So now if I got insertion sort over here, let's see the idea. Again, initially we got the same coloring notation here from before. Initially, nothing has been sorted. Okay? Now, we would like to grow the green area by one element. The way we grow it is by inserting, oops, again, just ignore that for now. Well, what we want to do is we simply choose the leftmost elements in the red area. And then imagine that we're going to insert it to the right spot, the correct spot in the green area. Okay, let me just tell you what the strategy is. I'll write it down. Pick the leftmost elements of the red area and insert it to the correct spot in the green area. Okay, that's the principle. But how do we do that? Okay, the very first insertion is trivial. Why? Because the green area is simply empty to begin with. How do you insert an element into some empty collection so that it's sorted? Well, just insert it, right? Because any collection with only one element is already sorted. Okay? So now let's see how that's going to work. Okay, the first insertion over here is going to be something like this. So the output from the first insertion is going to be, still we got 4 elements here. So now 3 is trivial, just to insert it. So we'll go simply put 3 over here. And then the rest remain the same, just like that. Okay, and now 3 becomes the green area, and also 143 becomes the 142. Sorry. Okay? Yeah, the first step is a little bit unclear. Let's see the second step. That will be a little bit more clear. Now, for the second step, let's follow the same principle. Pick the leftmost element from the left area. And now, how do we insert 1 into the green area so that the green area remains sorted? Currently, green is sorted. We want it to remain sorted. You have 2 options. Either you can insert 1 after 3, or insert 1 before 3. You got 2 options over here. Should be before, right? Right? So what you should do is, over here, 1, 2, 3. So what you should do is somehow 1 inserted before 3, and then you still got 4, 2 over here. So that's what you have. Okay, 1 and 3 here, and then you have 4 and 2 over here. Okay, insert to the left. Let's see the next one. Now, the next one, hopefully you can try to see if you can make it more general. If I have like this, I will pick the leftmost over here. So now, how many possible ways can I insert into the green? I can either insert it right here, I can insert it in the middle, I can insert it before the first elements in the green. Which one will be the right way to insert? This one here, right? So that it remains sorted. Okay, let's do one more. Okay, 1, 3, and 4. And now 2 is here. So now, so far we have got a green area that's almost there. Okay, and then it's 2 over here. Okay, one more. Can you actually tell me what would be the loop to write in order to insert? Can you come up with something like this? Let me just do one more example. That will be the last one. Okay, and then we can make it more general and we can talk about running time. So now we just need to grow 1 more element in the green area. So now, how many choices do we have to insert? Well, it can be either inserted after the last elements, insert it between the second and third, insert between the first and second, or insert before the first. 1, 2, 3, and 4. Which one? Which one should we, which option should we opt for? 3, okay, that's good. Okay, now, I know it's 3, but can you tell me how you would make it more general? If you have to write a loop, I'm just going through one example with you, but how would you write a loop to insert it to the right spot? Yes, go ahead. Yeah, somehow, yeah, conceptually you grow by 1, but let's say I already give you the green array, let's say. So how, let's say I go over the green array, 1 by 1, but how do you know where to actually insert? How do I know? You somehow you gotta compare each element, I agree, but when do you know where to stop? Okay, let's say this. Let me give you a little more hints. If I tell you this is the green array that you have to deal with, right? Let's say the way I go over the green array is backwards, let's say, okay? I simply go from the end to the front, okay? But how do I know that I should really stop right at this point and insert it? How do I know? Right? Huh? Something to do with values, I agree. Yeah, that's good. Okay, that's exactly right. Let me give you a little more intuition over here. We know that if you have the green area is such like this, some number over here less than or equal to some number here, less than or equal to some number here, and etc. Let's say. If I want to insert a number over here, let's say just b, okay? If I want to insert number b into there, it must be such that if I want to put the b over here, it must be the number before is less than or equal to, and the number after is larger than or equal to, right? That's kind of the intuition. You will see exactly that in the code. Okay, that's the only tricky part for the insertion sort. Okay, let's do that quickly, and then what I will do is over here, so now after that, the whole thing will just be green, and then what I will get is 1, 2, 3, 4. So we opt for this particular choice for inserting. Okay, that's about insertion sort. You can see it's not the same as selection sort. It actually works very differently, but they're also very similar, right? So now, before I generalize the diagram for you, how can you see the running time for this? Can you see the running time? Anyone? I'll try. Running time. I'll give you a little bit hints. The way we figure out the running time for selection sort is to see how much it will cost for each selection. The very first selection costs n. Second selection costs n minus 1. The pattern goes on until the last selection costs 1. n plus n minus 1 plus all the way to 1, we got n squared. What about insertion here? How much does the first insertion cost? 1, right? Because inserting just to the green area that's empty, just 1. What about the second insertion? Somehow you got 1 element over there. You can either insert after or before. That can be 2, right? Maximum, right? What about third insertion? 3, right? You got a 3 option. Let's say the last insertion. Basically, you got an n minus 1 array size. You can either insert, well, at the last, in the second last, third last, and all the way to in the very beginning. So you got n options, right? So now, the insertion sort is completely the opposite. So the arithmetic sequence you will get eventually looks something like this. And I'll draw some diagram to show you. It's something like this. For the very first insertion, it would just be 1, because the green area is just empty, trivial. And the second one, the green area is a little bit larger, so the cost to insert will be a little bit larger. And all the way to the very last insertion we're going to do. Basically, the green area is already n minus 1. So that means you will take n minus 1, something like that. And you can see it's exactly the reverse of what we had before, right? We used to have n plus n minus 1 all the way to n, 1. But here we say 1 plus 2 all the way to n minus 1. It turned out to be the same, even though they look very different. Okay? So it's going to be big O of n squared. Asymptotically speaking, is selection sort better or insertion sort? What are they saying? They are the same. Yep, the same. They're both quadratic. Before I draw the diagram, what does that mean? When I say a sorting algorithm is n squared, I'll just give you one example. If I got 1,000 integers for you to sort, in the worst case, how many primitive operations do you have to execute? Let me say that again. If the input size of A is simply 1,000, I got 1,000 integers for you. In the worst case, how many primitive operations do you have to execute? Well, plug in the number, right? 1 million. What about I give you 1 million integers? 1 million square. So you can see it doesn't really scale very well if you got very large input. So quadratic algorithm is nice, for small or medium scale input, but it's not so nice for large inputs. Okay, are we okay? Yeah. Now let me just, to make it complete, I'll just like to draw the diagram very quickly for you to summarize the insertion sort. And then we can go over some code together, okay? So this is what I like to do over here. So now for the insertion sort, you start with an array of arbitrary size that is going to be, is going to be totally unsorted. Okay? After the first insertion is going to be of the same size of the array, but now we're going to get exactly just one element in the green area, and the rest is just going to be unsorted still, right? So from here to here, we got exactly just one insertion, right? And then for the second one, it's the same. If you go all the way to the second last, and also the last result over here, so we know eventually it's going to be all green. Okay? So before the last insertion, how does it look like? That means we're going to get everything basically is sorted except for the last elements that is unsorted. And as we said, this is going to be the most expensive one. You want to insert that into an input array of size n-1. So this is going to be n-1. Okay? So that's how you figure out the math over here, up to n-1. Okay? Okay, any question about insertion sort, selection sort conceptually? Are we okay? Okay. Now, what I would like to do now is go over some code. How about this? I'll show you something on Eclipse first. I'll make the source code available to you today, and then I'll go over exactly how the code works quickly next Monday when we meet together. Okay, quickly. So now this is the code I'll give to you. So it's basically a class with just two methods. So it's called sorting. So we have selection sort, and over here, and also we got insertion sort. So we got two sorting methods here, right? Selection sort, insertion sort. It would be to your interest to maybe try to trace the code a little bit by yourself to see how these things work. They should correspond exactly to how I explained the two sorting algorithms in general. Okay? So selection sort, insertion sort. And how do we test the sorting method? Let me show you the JUnit method quickly. If I get to the JUnit test method here, so one is called test selection sort, the other one is called test insertion sort, or these two. And then I use the same input array, simply use 3, 1, 4, 2, right? And what I expect to have from each sorting is 1, 2, 3, 4. You can see in one case, I simply call selection sort. And the second case, I call insertion sort. And then I simply get sorted expected, and then whatever that's being sorted is the actual value, right? They should match in both cases. Okay, what I would like you to do before Monday, because on Monday I'm going to go over the code with you, they actually are rather sophisticated. This is the practice you would like to do by yourself. You would like to see exactly why the way things work in Java over here precisely correspond to the conceptual diagram I drew over here. Okay? Similarly, the way the Java code over here work for selection sort. Okay? Also, you got some nested loop over here, work exactly like the diagram I drew over here. Okay? That's the exercise for you. Okay? And then for lab test 2, as I mentioned, I'll give you the study guide Monday the latest. But before that, I suggest you work on lab number 3. So I think lab test